we're going to discuss RC circuits. What is so special about them? And what we, in all circuits which we've been discussing for the last week, right? In all those circuits, currents were constants all the time. It doesn't matter at which moment of time you look, current is going to be the same. 5 amps all the time. But of course, there are situations where current or currents are not constant. And this is the first example where current is going to change in time. And that's the first situation, which it's the first and the only case, not the only case, right? So, but for now, it's the first example where current changes in time, right? So again, that's the major point. That's the major point of this new material. And we're going to discuss RC circuit. So by the name RC, you can guess immediately that this circuit is going to consist of a resistor and a capacitor. And of course, naturally, if you start playing with this, start creating circuits out of these two elements, of course, you can identify two situations. In the first situation, you need to charge that capacitor. Originally it's empty, and then you want to charge it. Of course, in that case, battery must be involved. So in that case, you will have a battery, resistor, and a capacitor. Charging situation, it's a first situation. And that's what we're going to discuss first. And then, of course, the second situation, what if your capacitor is already full and you want to discharge it? And of course, you're going to discharge it through the resistor. Why? Because if you just connect plates over capacitor directly with pretty much without any resistance, most likely you'll just damage your capacitor, right, and create lots of mess, right? So it's better to slow the process down, discharging process. So it's better to put a resistor so that current will have a finite values, right, and you're not going to damage your system, right? So that's why resistor all the time is in the system to slow things down so that you wouldn't destroy the system, right? And the same here, we have in the charging case, usually people put a resistor, right? So to slow things down, right? And plus it allows you, it gives you additional freedom to control how fast you can charge or discharge your capacitor. Okay, so those are two situations, charging and discharging. We're going to start with the charging case. I'm going to basically I want to go through everything. Why I want to derive it, because there are plenty of physics to discuss. Mathematical part where we will have to solve differential equation, no, we're not going to discuss it. I will just give you the answer. But physics part of where we need to discuss physics, yeah, that will be applied. Okay, so now, yeah, I already drew the circuit. So we have a battery, strong battery, right? Positive electrode, negative. And originally, at the initial moment of time, the capacitor is empty, right? Capacitor is empty. And here, of course, you can imagine a switch. Let's say you close the switch. And of course, current starts flowing. Somehow current is going to change in time. For some students don't see immediately behavior of the current, or actually they see, but that behavior is wrong, right? But anyway, we will see the actual behavior of the current. But anyway, so first, capacitor is empty, and then of course capacitor starts getting fuller and fuller and fuller, and eventually it will be full. When capacitor is full, it means what? Current will stop flowing. Right? And when it happens, when potential difference across the capacitor is going to be equal to the potential difference created by the battery. In that case, when potential differences are equal, current will stop flowing, right? And pretty much the process of charging will be over. Right. Okay, so then effectively we need to analyze this circuit. And again, what does it mean, analyzing circuit? It means that we need to find everything that we can. So it means that we need to, okay, let me write. And okay, you know what? Yeah, let me analyze it. And what does it mean? We need to find how current changes in time, and it will be a function of time. Then how charge in the capacitor changes in time. You know what? Let me write that charge over here, Q, as a function of time. Current, okay, I will show in a second current. Then what else we can ask for? What about potential difference across the resistor? And what about potential difference across the capacitor? So delta V sub C and delta V sub R. So these are possible questions that can be asked. But of course, you must feel that all these quantities are connected, right? It means what? If you, for example, find one of them, for example, current, you should be able to find the rest of them reasonably easy. Or you can find, for example, charge, how charge, you can find the function how charge changes in time. And then once you know that, you should be able to find current and you should be able to find these delta V's. And actually, I'm going to show how it can be done. And we're going to find charge. And then we will be able to get the rest. Okay, so then, before, when currents were constant, it didn't really matter at which moment of time we're going to look at the circuit because current was constant all the time. But now everything is in dynamics, everything changes in time. So we need to say, specify at which moment of time we're going to look at this circuit, right? And we're going to look, and that's what I drew, at an arbitrary moment of time t. I want to write the equation at some arbitrary moment of time t. Basically, t is the variable, right? And then, of course, as a result, we're going to get functions. And yeah, we can analyze functions of time. And then we can analyze those functions to see what happens at this moment of time, that moment. So what I drew over here, it's an arbitrary moment of time. Right, and you see, capacitor at that moment of time is somehow filled, right? Not completely empty, right? Somewhere in between, right? Some amount of charge is inside. All right, so then, which method can be used? Kirchhoff rules, they're universal. So let's just grab them and try to use them. The only, what is new, we never applied Kirchhoff rules in the presence of the battery, in the presence of the capacitor, in the presence of a capacitor. You see, all the time over here we used, we had resistors, batteries, but we never had a capacitor. But it's not a big deal. We can easily write contribution delta V to the loop equation for the capacitor, and you will see how. Right? Okay. Anyway, Kirchhoff rules, and there are two of them: junction rule and loop rule. Junction rule. Since we don't have any junction points, so it's not applicable. We have only one current, right? So junction rule is not applicable. So we have to apply loop rule. So let me write. So loop rule, sum of all potential differences across the loop must be equal to 0. And you remember preliminary steps which we have to make in order to start applying loop rule. Yeah, no junction points. So the first one is out. The second one, I picked direction of the current and introduced the introduce the currents. Right now, we have only one battery. We don't have to guess a direction of the current. We can tell immediately what will be the direction of the current from plus to minus, right? So over here, we can tell immediately that the current is going to flow this way. So that's our current is a function of time, and here the same. So we have current and now travel direction. So let me pick the same direction as the direction of the current. That's what I usually do. So that's travel. Okay, so now we're all set in order to start writing the equation, loop equation. Let me check if I mentioned everything. Yeah, now it's time to start writing the equation. And you know what? First, I will write like this, just in general. So delta V of the battery plus delta V of the, okay, across the resistor and plus delta V across the capacitor equals 0. So without specifying, just delta, delta, delta. And with this, we know how to deal with these two contributions. But what about this? Delta V across the capacitor. So in order to uh, uh, in order to write what is delta V, first of all, let's recall the definition of capacitance, right? So you remember that capacitance we introduced in this way: C equals as Q divided by delta V over C. So from here, we can get the expression for potential difference across the capacitor. It will be equal to Q over C. So that's what we're going to use to write the absolute value of that contribution. But what about the sign of this delta V across the capacitor? So you see, we travel this way, right, from top to the bottom, right? So this way across the capacitor. So this will be our final point, right, when we are crossing the capacitor, and this will be our initial point. So this final point is negatively charged. It is at lower potential. This point, I mean this electrode, is positively charged, so higher potential. So delta V, V final minus V initial, is going to be negative. Is going to be negative. So this contribution over here is going to be negative, right? So you know what? Yeah, so this is basically the formula which we use. And of course, I can write that delta V sub C will be equal to minus Q over C. So that will be the contribution. So you see, even without introducing original mnemonic rule, yeah, we could write this contribution. Okay, so now let's write the equation explicitly. So across the battery, so we're crossing from minus to plus, so contribution is positive, rule number 1. So it will be plus EMF. Then across the resistor, travel direction, current directions the same, so contribution must be negative, minus IR, minus I times R. Then across the capacitor we just discussed, final point minus initial, lower potential minus higher potential, contribution is negative, so it will be minus Q over C. And it must be equal to 0. Okay, so that's the equation. Now let's look at this equation carefully. Again, you need to remember EMF, R, and C are given values, right? So you assembled your circuit, so you know them. Unknowns, current, and charge. Two unknowns. How many equations? Only one. And we don't have any equations. We have only one loop, no junction points, so no chances of getting the second equation. So we have only one equation, but for now we have two unknowns. Of course, it's unsolvable from a mathematical point of view. But let's look carefully. Current and charge are two unknowns. Are they independent or are they dependent? Of course, your gut's feeling should tell you that there must be a connection between them. There must be a relationship between them. Look, because this charge in the capacitor, Q, it's a charge in the capacitor, increases at the expense of what? At the expense of that current. Current flows in the capacitor, capacitor gets full. There must be a relationship between them. Let's digress for a few minutes and find that relationship, because without that relationship, we wouldn't be able to solve. Once we find that connection, we will be able to replace, for example, current with something in terms of Q. And in that case, we will have one equation with one unknown. So right now we need to digress and find that relationship. And then we'll get back to this equation. And of course, that will be equation which we will have to solve. Okay, so now which way I wrote it? Okay, I wrote it like this. I and Q are dependent let's connect them. Let's connect them. Right. Okay. So basically, I will put here a small bullet. It's sort of like a digression. And then at some point, we will get back to this equation. You know what? Even let me frame this equation. With green, it's not the last one. It's not the final. But we need to mark it that we will have to get back to that. Right. So how are we going to connect them? These two quantities. You know what? I'm going to draw this part of the circuit. This part of the circuit. Let me just zoom in on a capacitor and this part of in this wire. You will see. I just want to get into the details of this connection. Usually books say something like this. It's obvious that since charge in the capacitor increases at the expense of the current, so as a result, it's obvious that current equals dq over dt. Yeah, I can feel that. I can to some extent buy it, but I was not completely happy with that, especially when we get to a discharging situation. Actually, the relationship between the current and the charge, there is a minus between that. And again, those words which books sort of pronounce, right? I was not completely happy. So as a result, I came up with what I'm going to present to justify the connections between these two quantities. So let's zoom at the capacitor and this part of the wire. I'm going to draw it like this, right? So this will be my piece of wire, right? And this is my capacitor, right? So this is C, capacitor, right? Which has charge Q, right? And let me denote Q small. It's when the charge, okay, when charge is inside of the wire, we use Q small to denote that charge. I will write the charge in the wire. And Q capital, of course, it's a charge in the capacitor. Charge in C, in the capacitor, right? So if Q small charge in the wire, of course, we can write down expression for the current. Of course, current is in the wire. So, of course, current is what? By definition, it's a dq over dt. So what does it mean, basically? Let me just recall. So it means that if you take, for example, here cross-section, this cross-section, right? You remember we discussed the definition of current, like runners, current of runners at Boston Marathon. Just count number of runners crossing. So it's here the same, right? So if you observe over the period of time dt, and let's say this amount of charge dq cross this cross section, then that's that. Then if you divide dq over dt, that's the definition of the current. So that's what we have here. The amount of charge dq, this crossing this cross section in the period of time dt. So if you divide them, you will get the current. Okay, great. So now, where does this charge? Okay, where is this charge going to be after some short period of time? Of course, it will flow and it will end up in the capacitor, right? Because the current flows in the capacitor. So after some period of time, of course, it will end up in the capacitor. So now dq will be here. So that's that charge which was in the wire after some short period of time will end up in the capacitor. Doing what to the charge in the capacitor? This charge in the capacitor will go up. It's like, no, 5 people entered the room. So number of people in the room went up by 5 people. Logic is trivial. Logic is banal, right? Okay, so now let me write that down. So which way I wrote? Okay, let me write this way. As dq, okay, dq small arrives. Okay, let me use passive arrived. Okay, let me write this way. When dq arrives, the charge in the capacitor increases. Right? So it means I can write what happens with the charge inside of the capacitor. It means that Q final equals Q initial plus that charge which just arrived. Again, the logic is trivial, right? So if in a room there were, I don't know, 20 people, initial amount of charge, and then 5 new people arrived, then of course the final number of people will be 20 plus 5, it will be 25 people in the room, right? So that's what I wrote, just charge from the capacitor, from the wire arrived into the capacitor. The amount of charge went up in the capacitor. Okay, so yes, logic is trivial. And of course, from here I can, let me solve it for dq small. So dq small equals to q final minus q initial. Okay, so now let's leave this for a few seconds. Just forget about this. We came up with this conclusion, and now let's look at just from the other side. Let me write from the other side. Basically, definition of dq capital. Again, as I said, let's forget about this for a second. Now let's look just from the mathematical point of view. What is dq capital? Any like delta q, dq, it's all the time final value of something, in this case charge, minus initial value of this, in this case of the charge, right? So as a result, we can write, so dq capital equals to q final minus q initial. And now let's compare these two conclusions, these two results. So what can we say? How can we relate q small and q capital? They equal dq small equals to dq capital. Let me write it here. All right. I know I wouldn't be able to fit it. Okay, I will write over here underneath. So dq small equals to dq capital. You can tell me, you can look at this and say it seems like obvious. Not so obvious, especially when you look at the discharging situation. And you can look in my notes, right, at home, right? So I ran exactly the same analysis for discharging case. And of course, over here, you will end up with minus. And so far, again, what books usually provide as an explanation, I wasn't happy with that explanation. They would say something like, for discharging case, it's obvious that since current increases at the expense of the charges inside of the capacitor, as a result, there is a minus. Kind of, yeah, I feel that it must be correct, but it never made me happy. So as a result, that's why I created something like this, in order to get all those pluses and minuses without some guts, without using some guts feelings. Right? So now look, how can we use this? So we can grab this fact and plug it into the definition of current, and as a result, we're getting what? So current, as a result, after substitution, we get equals to dq over dt. And again, what's the difference? Here, charge was in the wire. Now it's a charge in the capacitor. And again, for discharging case, there will be minus over here. For charging situation, it's positive. Again, it's just quantities in a different part of the circuit. This is current, it's in the wire. This Q capital, it's in the capacitor. Right? So that's how they are connected. And you know what? I need to frame them with red, because when we solve the problem, find Q capital, these will be used to find the current. Right? Okay. Basically, now I finished with this bullet. So now we finished our digression. So now we need to go back to our equation. So now I will write, so back to the equation. So now we managed to connect them. So now we know how I and Q are connected. So now I can even probably use this green to show now we're going back to this equation. So it will be EMF. Then now instead of current, I'm going to use this dq over dt. So minus R times dq over dt minus q over c equals to 0. Ta-da! So now one equation, one unknown q. Now it can be solved. But now, of course, we have a differential equation, right? First order differential equation, right? So, and of course, it's a first time we see differential equations in this course. Right. Okay, so now what needs to be done now? We need to make it look nicer. Basically, at this point, yeah, the equation now, you just need to solve it. But usually, anyone who is in physics, right, and especially books, when you get the equation, now after this, you start making, you're trying to make it as nice as possible. So now it's just cosmetic changes. So now let's write it in a nicest possible form. Although nothing wrong with that, but it just looks ugly. We just need to, I don't know, comb it slightly, put some makeup, right, so that it would look nice. So what I'm going to do in order to make it look nice, I'm going to divide the whole equation by minus r. Pretty much it means that I'm going to divide each term of this equation by minus r. Basically, I want to get rid of any factors in front of this derivative. That's the goal, right? Okay, let me, all right, I hope I will be able to fit. So it will be dq over dt, right? Then, which term I wrote next one? Okay, q over rc. Okay, why not? So then this term, minus give us plus, and r times c. So downstairs we're going to have rc, q divided by rc. Okay, just a second. Let me write this equation, and then we'll have a break. So plus q divided by rc. And then this term, if you divided it by minus r, of course you will end up with minus EMF divided by r. And it is equal to 0. But you know what? These two, okay, here I have RC, here I have R. You know what? Let's bring these two terms to common denominator. Right? Multiply this by C and divide, multiply by C and divide by C. Let's bring this last term to the same denominator as the previous term. Right? Okay, and as a result, you see now we have some construction, interesting construction, R times C. And you remember what? You build the circuit, you know R, basically R is given. Also, you inserted some capacitor, so C is given. So basically this product RC is some kind of intrinsic property of this circuit. Right? So if you build the circuit, that is just basically a given parameter, some constant will be, right? It makes sense in order to simplify your life here, give it a special name. Time constant. It's kind of surprising that when you multiply resistance with capacitance, you're getting units of time. If we have time, I will show that it's true, right? If you multiply resistance and capacitance, you will end up with a quantity which has units of time. It's not kind of obvious, but yeah, it is. So now let's denote, and after this we'll have a break. Denote tau. Wait, it looks not straight. All right, let me. RC. RC. It's called time constant or RC time constant. Okay, you know what? Let me put 3 lines, basically by definition. Right, so it's called time constant. Right. Okay, and of course I have it has to be framed because it's one of the most important parameters when you play with RC circuit. Basically, it tells you how fast, we'll see, how fast this or that RC circuit charges or discharges, right? Okay, at this point, let's have a break. After introducing RC, we will have to look, what the hell was this term, EMF times C? We need to analyze and realize what is that. Again, because look, EMF is given, you put some battery, C is also given. It's some kind of a new constant. Also, of course, probably have a different meaning, but again, it will be a constant describing this system. Like here, we introduce time constant. Now we need to realize what is EMF times C. So after the break, we'll do that. And basically at that point, the equation will have the nicest possible form. We're not going to solve it. I will just write down the answer. And if you want to look at the solution at the end of the presentation, at the end of the slides, I created a slide where I solved the differential equation. So as I said, now let's identify what is EMF times C. Right. Again, it looks like it must be some intrinsic parameter of the system, because it means if you build this circuit, this constant is some basically number. Okay, so now let me write that down. EMF times C, and I will put a question mark. What is that? Okay, in order to understand what is that, let's again recall definition of capacitance. And let me write it in this way. Q equals C times delta V. Right? Okay, let me write. So Q, which way should I write it? Just a second. Yeah, you know what? Let me first write definition of capacitance, and then only it will be clearer. So Q divided by delta V, right? So the definition of capacitance, let me frame it, right? And so, of course, from here we can write Q. And again, you remember Q, it's a function of time. C is a constant. Wait, delta V, not delta T. Delta V, right? So it is equal to C times delta V. And of course, delta V is also as a function of time. It's a potential difference across a capacitor. C is constant, but Q and delta V, they're functions of time. So that's what I wrote. So now let's look at this when t goes to infinity. Let's just wait for a long period of time, t goes to infinity, and what we are going to get here in this expression. So what will be what will happen to the charge if you wait long enough? This capacitor will be fully charged to the maximum possible charge that it can hold under these conditions, right? So if you wait long enough, delta Q will be maximum. So in this case, I can write, so Q will be equal to Q max. Again, at this moment of time. Then what can you say about the potential difference across the capacitor if you wait long enough? Right? Some of you should be able to see what will be the potential difference across the capacitor when capacitor is fully charged. Of course, at that moment, current will stop flowing, right? So at that moment, potential difference across the capacitor must be equal to the potential difference provided by the battery. Basically, when potential difference across the battery equals to the potential difference across the capacitor, current will stop flowing, capacitor is fully charged, right? So, and that of course happens at t equals to infinity. So at t equals to infinity, delta V across the capacitor equals to the EMF of the battery. Okay, so now I can write that. And of course, delta V will be equal to the EMF. So as a result, we're getting, so Q max equals to C times EMF. So pretty much that's our this constant which we're trying to identify. So EMF times C is just the maximum possible charge in the capacitor. So this is just Q max. So this is just Q max. Right. Okay, so now we are ready to write down the final form of the equation, which I'm not going to solve, which I'm going to just write, and I'm going to write the answer. So this is our equation. So it will be dq over dt. Then let me write it in this way. I will take minus outside, right? Yeah. So it will be minus, and I'm going to write it like this. Q max, it's from this, then this Q minus Q, and divided by the time constant equals to 0. So it's exactly the same. Like, look, if you open this bracket, of course, this minus will be next to Q max, this minus, and this minus with this minus is going to give us plus, so you're going to get Q over tau, right? So this equation and that equation are the same. So let me frame it, but with blue, because it's a equation, but not the solution. And it's not the complicated differential equation. You can solve it, right? For those of you who are familiar with differential equations, again, if you want to look at my solution, it is at the end of the presentation. It's already in the blackboard. So the solution, let me write it down. I will probably write it here, yeah. So the solution will be equal to Q as a function of time equals to Q max and 1 minus e to the power of minus t over tau. So that's the function. That's how charge in the capacitor changes with time. Okay, I almost erased this. Right. So now what's next? We just need to analyze it. First of all, let's plot it, right? Then the meaning of Q max, it's obvious, but the meaning of tau, we will also have to realize the meaning of that time constant, right? But for now, let's plot it. Let me do it here. So let's say this is Q. This is time, right? And let's see at sort of critical points, endpoints. So first of all, what happens? What's the value of the charge when t equals 0 at the origin? T equals 0, so this will be e to the power of 0. It's 1. 1 minus 1 gives us 0. So the amount of charge at the initial moment of time is 0, as it should be, because that's our sort of initial situation, initial conditions. First, capacitor is empty, right? And our function gives us that point. Then, what happens when t goes to infinity? When t goes to infinity, t goes to infinity, you get e to the power of minus infinity. It's 0, right? So this term is 0. We're getting, as a result, we're getting only Q max times 1. So at infinity, the amount of charge on the capacitor is maximum. So let's say it's this over here. So this is Q max. And let me draw this line, basically asymptote. And our function reaches that asymptote when t goes to infinity. So effectively, we're going to have something like this. So current is going to increase like that. Okay, not current, charge, sorry. Charge in the capacitor. Charge in the capacitor. That's what we found. Right. So first, at the initial moment of time, the amount of charge increases faster than slower, and eventually it will reach maximum. And of course, it will stop increasing. Then, so that's how it depends. Now, what's the meaning of tau? Let me put tau and question mark. Let's try to understand the meaning of tau. Okay, in order to see the meaning of tau, we just need to look. Okay, what is tau? Tau has units of time, so it means let's look what happens at that particular moment of time when t equals tau. Okay, it's probably somewhere will be here, let's say. So what happens at that moment of time? So when t equals tau, what are we going to get in terms of q at tau? Here you have e to the power of minus tau over tau. It's 1, so e to the power of minus 1. So effectively you're going to get, I'm afraid that I will not be able to fit everything, 1 minus 1 over e. That's what you're going to get, right? Okay, I abbreviated m, just m for max, right? Because I was afraid that I will not be able to fit. Right. So now if you calculate this 1 minus 1 over e is 2.7, right? You remember? So if you calculate this, you will get 0.63. So basically, the amount of charge at that moment of time is 0.63 Q max. Basically, it's a moment of time when the charge in the capacitor reaches 63% of its maximum value. Basically, that's the meaning. So now let me show that. And this point is 0.63 Q max. Right, so okay, let me show that. It's that. So that's the meaning. And again, time constant, this time constant, it's a very useful parameter because it allows you to tell how fast, in this case, capacitor is charged. In the case of a discharging, it will tell you how fast capacitor gets discharged. And if you have, for example, two circuits, right, and you want to compare which one is going to discharge or charge faster, compare their time constants. The smaller time constant, the faster that capacitor is going to be charged or discharged. Of course, the longer time constant, of course, the longer it takes for the capacitor gets charged or discharged. Right? So that's the meaning of, okay, that's how you can use the time constant, of course. So what else I need to mention? No, that's it. So pretty much we solved for one of these quantities. We found Q capital, the charge in the capacitor. But if you're interested in the rest of the quantities, I told you they are connected. And connection is not that complicated. So first of all, how can we find current? Current flowing through this resistor, flowing through in this circuit. Very simple. We spend this, we spend here like 5 minutes basically finding the relationship between Q and current. And again, for a discharging case, there will be minus over here. So that's how we can find current. Right, so then, okay, I can put a new bullet. So current as a function of time equals to dq over dt. Okay, so let's differentiate it. I said minus, and it will be for the discharging case. My brain started jumping to ahead of me into the next situation. So it will be you just need to differentiate the function which we just derived. Q max 1 minus e to the power of minus t over tau. Right, and conservation of brackets, I need to put additional bracket, yeah. Okay, differentiation, at this point, you should be very comfortable, right? Of course, first you need to differentiate Q max times 1. It's 0, of course, when you differentiate constant is 0. Then, when you differentiate this, of course, you will get minus Q max because it's a constant factor, minus Q max. And then you need to differentiate this function. So exponential function, when you differentiate it, that minus will pop up and that tau. So you'll get times minus 1 over tau. And exponential function survives every time differentiation, right? So that will be the derivative. Minus and minus give us plus. And then we have Q max over tau. Q max, where is Q max? Here. You know what? I should frame it also. Right. Right. So that's our Q max. So let me write it over here. So it will be, Okay, let me write underneath. So it will be EMF times C divided by tau. What is tau? By definition, it's RC. RC, and times that time dependence. C goes, and we're getting, so what is EMF divided by R? EMF divided by R, it's the current at the initial moment of time. When you close the switch, that's what you're going to get. So it will be I naught and E times E to the power of minus T over tau. So that's how current changes in time. Okay, in a second I will switch to presentation in order to discuss this current. Then, how can you, for example, find delta VC? Right? Because again, as I told you, all these parameters, okay, quantities are connected, deeply connected. Right, so then, wait, wrong color. So next, what if you want delta V sub C? So how can that be done? We already used it, right? So here, delta V sub C, we found function which describes how charge changes with time. So that Q divided by C, right? Q as a function of time divided by C. Okay, it's the absolute value of the potential difference. Then what if you want to find, for example, potential difference across the resistor? You can either EMF and subtract this and subtract this, and it will be potential difference across the resistor, or you can just use Ohm's law, because now you found current multiplied by R, and that will be potential difference across the resistor. So you see, once you found a Q, finding the rest is quite simple, right? Okay, so that's what I was planning to discuss on the whiteboard. Yeah, let me check if I mention everything. Looks like yep. And now let me switch to the presentation in order to discuss this, how current changes with time. Okay, so that's the function, how current changes in time, which I just derived, right? And this is the plot, right? So let's just discuss the behavior of this current. Again, if you plot this function, right, so that's what you're going to see, right? So let's discuss from the point of view of electrons, what do they see? So first, when the switch is open, at the initial moment of time, there is no current, switch is open, capacitor is empty, battery is fully charged, right? So electrons is sitting at the negative electrode, right? Crowded electrons, right? You remember they hate each other, they repel each other all the time, right? So that's the initial situation, right? Then you close the switch, and now then what do they see? They see at sort of the wire like a tunnel, and they see at the end of this tunnel the bright light, right? Empty capacitor, completely empty, lots of free space, no one is there, right? And here they are in this crowded room of the negative electrode, right, hating each other. Of course, what are they going to do? Of course, immediately tons of these electrons will start running towards that empty capacitor to get as far as they can from the rest of the electrons, right? As a result, immediately, if you start measuring current, you will see that current jumps immediately to the maximum one. And that's what we observe over here. First, current is maximum because these electrons like crazy will start running towards that bright light, trying to get to run away from their friends, right? Right. But then, what will happen then? What happens then? So new electrons arrived to the capacitor. And now what will be their behavior towards the new electrons coming? Of course, they're going to repel them. Again, they're still negatively charged particles. Of course, they will start repelling the new coming electrons, right? So for the new electrons to arrive, it will be slightly more difficult. And the more electrons arrive to the capacitor, it's more difficult for new electrons to arrive, because lots of pushing from these electrons. It reminds me like the situation in New York somewhere at the end of 19th century, right? I mean mid of 19th century, right? When immigrants who arrived yesterday hated immigrants who were arriving today, right? Because again, that was a tough fight for jobs, right? So there were lots of even fights, right, between different ethnic groups, right, and so on. There were lots of mass back then. So of course, those who arrived usually yesterday hated those who were arriving today, because yeah, this will increase competition on the job market, right? So the same like these electrons, those who arrived earlier hated those who were arriving later, right? And they're trying to push them away, create some resistance, right? So as a result, you see what happens with the current. So it's more and more difficult for new electrons to arrive to the capacitor, and as a result, number of electrons are getting smaller and smaller and smaller and smaller and smaller. And eventually, when the capacitor will be fully charged, it would be impossible for new electrons to come there, to arrive. So of course, current will disappear. And you know what? Once I remember I was when I started teaching, I was watching the movie, right? Occasionally I do it. And I watched that movie with Tom Cruise and Nicole Kidman. I think it's called Far and Away. Let me call it. Is it Far? No. Yeah, the Far and Away. And in one of the episodes, they had what is called the land run. So what's the story? It's in the Oklahoma territory. Back then, it wasn't part of U.S. It just, right? I don't know, whatever the status was. But anyway, according to the history, how the land was distributed between or among farmers. So they created a race, horse races, right? And whoever arrived, arrives first to the land. So that person can claim, okay, this is my land, this is your land, right? Okay, it's fun, right? Creating races to distribute land, but you know what? I don't know. I find it hard to believe that that's how land would be distributed, right? But anyway, according to the history books, that's how land was actually distributed, right? And let's look at the movie, at the episode, how it was done, right? Okay, so let me. You know what? First. Let me. I already opened it up. I just need to. Share it, okay, with computer sound. Where is it? Okay, here it is. Right, so let me open it on a full screen. Can you see it?
Yes.
Yeah, great. Yeah, it should be. Okay. Since I don't share quite often slides or, okay, I mean videos or something else, so I was. So you see what happens? Tons of farmers line up along this line, starting line, all right, and waiting for the gun. Basically like electrons sitting in the battery, hitting each other, right? And here at the initial moment of time, okay, when the gun fires, right, they see this empty land, right? Like capacitor, empty capacitor. So for farmers, it was like empty land, right? Where they can live, where they can grow their, whatever, right? Or grow whatever, I don't know, cattle or wheat, right? Or corn, right? So of course, they have lots of attraction, strong attraction towards that land. Of course, there's first at the initial moment of time, if you look at the cross section of this race, of course you will see that number of people, number of farmers per unit time will be the largest possible. So the initial current is the largest, right? You see, if you imagine the cross section, right, through this line, of course, number of people per unit time will be the largest, right, during this process. But of course, later on, right, let's say a few minutes later, all right, so let's say a new family will arrive with, on the horse, right, on this carriage. of course, the husband will say something like, well, so what's the point of going there? Chances that we're going to get land is minuscule, right? But maybe after being punched by his wife, he would actually decide to go, right? Agrees to go. But let's say after 30 minutes, even the wife will agree that yeah, there's no any chances that we're going to get any land. It will be most likely occupied completely, right? So you see, behavior of these farmers in an attempt to get land is exactly, I'm not saying similar, it's exactly the same as behavior of electrons charging the capacitor. Again, I'm not insulting us as human race, right? But you see, social dynamics of us human being is exactly the same as dynamics of electrons. And we shouldn't be surprised because, yeah, we're part of the same nature. God created nature in a very similar way, just scaled different, right? Scale it in a differently. And that's why lots of mathematical equations are used to predict, I know, behavior of a crowd on a stock market, right? There are actually well-developed theories, right, like Elliott waves, where you can predict what is going to be next, and so on and so forth, right? And behind of all of that, mathematical equations, which we also use as physicists, right? Yeah, when I was watching this movie, I kind of, damn it, wow, it's exactly the same what electrons do, exactly the same. Yeah, so they're on the way to charge the capacitor with some catalyst. Okay, it should be enough. And of course, you see with time, of course, number of the people paying the time, sourcing the light, smaller and smaller and smaller. Okay, enough. All right, let me stop sharing this. Here it is. Yeah. And you know what? The more I teach physics, right, and trying to compare with our everyday life, just these dynamics, right, the more similarities I can find. Sometimes even the amount of similarities just scares me, right? But some of them I show, right? Anyway, so now if you, for example, forget about how current changes in time, just recall this episode, this movie, right? So first, lots of farmers running, right? And then as time goes by, of course, the number of them will get smaller and smaller and smaller. And eventually, of course, there's no any point because the land, the old land will be most likely taken, right? Okay, so that's what I wanted to discuss. And now I think, yeah, of course, you see time constants, right? You see R. Yeah, actually, yeah, I should have mentioned that. Now I just realized. The meaning of time constant tau, RC. You see, when we looked at charge, right, amount of charge in the capacitor, so at the moment of time tau, what happens? Charge in the capacitor reaches 63% of its maximum value. But when you look at the plot of current, what happens? At the moment of time tau, current reaches 37% of its maximum value. Right, again, it depends on which plot, with which plot you work with. Capacitor, 63% of its maximum value, and here 37% of its maximum value. Right. All right, so what's slides forward? Just a second. Yeah. All right, and yeah, I compared, right? So I took a snapshot of the screen, right? So before the switch was closed, so electrons are waiting, so farmers are waiting, right? So then at the initial moment of time, lots of electrons running, lots of farmers running, and then of course, and then of course with time it goes down. Now the question for you, the first one, which is doesn't require any calculations, just conceptual analysis. There. So RC circuit, you see, we have a battery, but now instead of EMF, V naught is given. But again, what a big deal, right? So if you know the meaning of epsilon naught, if you see V naught, it should not scare you. Then, of course, there is a switch, which will be closed at the initial moment of time. Initially, capacitor is empty, so you see the charging situation, which we just discussed, right? And so instead of a resistor, now there is a bulb. But what's the difference between a bulb and a resistor? That bulb also produces light. Yeah, it still has a resistance, but also at the same time it produces light. So now, when you close the switch in this RC circuit, can you describe the behavior of this bulb in terms of producing light? Behavior of this bulb in terms of producing light. A, no light. Second, B option. First, it's when you close the switch, first it's bright, and then it gets dimmer and dimmer and dimmer. Then C, first it's very dim, and then it gets brighter, brighter and brighter, and warming up. And D, steady bright. So give it a try, and then of course I will discuss that. So what's the time I left? Okay. Production of light. You remember? It's basically we convert electric form of energy into into the light, right? Different forms of energy, right? And you remember how we described it? I think it was in the previous class when we discussed electric power, right? And you remember we introduced the formulas which can be used to calculate that electric power. And for this situation, I think will be the most convenient I squared times R. P equals I squared times R. R of the bulb, we assume it stays constant, right? It slightly changes because it's getting warmer and warmer, right? But we can assume it's constant. So as a result, power, amount of light produced by the bulb basically depends on how current changes in time. And how current changes in time, we just discussed it. It's a charging situation, and we just spent almost half a class deriving that. And here's the plot, and we just watched the movie, right? Basically simulation of behavior of electrons, right? Using Hollywood actors, right? So you see, so what happens, and of course R constant. As a result, basically, this is the plot how power is going to change in time. Of course, if you scale it by multiplying it by R, right? So first, as a result, it means a bulb is going to be bright, and then as time goes by, of course, that brightness is going to get smaller and smaller and smaller. So first it is bright, and then it gets dimmer and dimmer and dimmer and dimmer. So that is the option bright and then dim. It's option B. Yeah, it's option B. Right. So that's how we should analyze it, right? Again, the goal of this question is just again to emphasize on the behavior of the current, because this dependence is not completely intuitive, because some students think that when you close the switch, first current is 0 and then it's growing, right? That's usually the first response of students. But you see, it's not. First current is large, and then it decays exponentially. Right. So then, next question. We have two RC circuits. You know what? No. I cannot ask the second question. Okay, let's switch back to the whiteboard, and I want to now discuss discharging situation, because the rest of the questions and the problems are about discharging case. And if we don't discuss discharging case, it's not fair, of course, to ask questions. Right. Okay, so let me switch to back to the whiteboard. I'm not going to derive anymore. I will just basically present the key points and key results. Important results, most important results. Okay, I will probably be able to fit it here in this part of the board. Yeah, let me turn off the filter. Okay, so now let me put a new big bullet and write something, a discharging, RC circuit discharging, RC circuit and discharging case. So for this charging situation, now battery is not needed. So now initial situation, capacitor is full, right? Switch is open, resistor is connected. Of course, a resistor must be there to slow things down, otherwise you'll just damage your system, right? And then you close the switch, and of course, a current will start flowing, and of course, charge in the capacitor will start going down. So let me draw the circuit very quickly. So, of course, circuit is simple. So this is a capacitor, fully charged. Then the resistor, of course. Right. So let me label it. It's C. This is R. Right. Again, charge in the capacitor, it's a Q. And again, it's a function of time. Let's assume that the upper plate is positively charged. The lower plate is negatively charged. Right. And current, of course, is going to flow from plus to minus. Okay, from positive electrode of the capacitor to the negative electrode of the capacitor, right? So this will be the current I. And again, it's a function of time. Right. Okay, and so what? In order to analyze the situation, again, Kirchhoff rule, right? Loop rule. And of course, in order to apply that, you'll have to pick the travel direction, right? And what are you going to get as an equation? So, okay, let me write first. Delta V across the capacitor plus delta V across the resistor equals 0. So delta V across the capacitor, positive or negative? Look, this will be our, so we're traveling this way. So this is our final point, right? So this is our initial point. So the final point is positive, so it's at higher potential. Initial point is negative, it's at lower potential. So if you look at delta V, of course, it must be positive. And absolute value of that delta V is Q over C again, right? But positive now. So it will be Q over C. Then contribution from the resistor, again, directions are the same. So contribution must be negative, minus I times R and equals to 0. So that is this equation, basically, right? Okay, similar stage. And again, the same, one equation, two unknowns, I and Q. Of course, your gut's feeling again should tell you that Q and I are connected. How connected? Books usually say something like this. It's obvious that current, since current increases at the expense of charges inside of the capacitor, then it's obviously, and they write immediately, so that current equals to minus dq over dt. I was never happy with that explanation. As a result, I usually run similar to this analysis. Again, if you want to look at that, you can see it in my slides, right? You can see it, but I'm not going to do. But it's very, very similar. But now over here you will get minus, and as a result, the relationship between the current and the charge in the capacitor through the minus. Relationship is through the minus, right? And again, it's very important because then once you solve this equation for Q, this equation can be used to find current, like over here, there, right? So of course you will have to differentiate, but with the minus in front. Right, so then of course this can be solved for Q, right? So let me put something like this. And as a result, Q as a function of time equals U naught and e to the power of minus t over tau. So that's how, again, if you take this, plug it in this equation, it will be again first order differential equation. Again, it's a very simple differential equation. For anyone who is familiar with differential equations, it shouldn't be a problem to solve it. And so that will be the function how charge in the capacitor changes in time. And again, if you plot it, you see it's an exponential decay. And time constant, the same time constant are C. All right. So if you plot this Q versus time, so this will be an exponential decay. So first, at the initial moment of time when t equals 0, charge is maximum Q naught, and then it decays exponentially, going to 0 when time goes to infinity. And again, the meaning of time constant, meaning of tau. If you look what happens at tau, you will see that it's just a moment of time when charge reaches 37% of its maximum value. Right, 0.37 of Q naught. So that's the meaning of tau. Again, the shorter, the smaller time constant is, the faster capacitor gets discharged. Right. And then, of course, if you take this and plug it into there, into this relationship, you will get how current changes in time in this case. So let me put this by the first bullet. Now the second bullet for the current. It will be again I naught e to the power of minus t over tau. Right. Again, if you plot will be very similar, but instead of Q, it will have current. So I versus time. And again, the plot will be very similar. But now this is I naught. This was Q sub 0, that is I sub 0. Again, you see, behavior of the current in both cases the same. In the case of a charging and in the case of discharging. Exponential decay. First it's maximum and then it decays exponentially, but charge behaves differently. Here you see, during the charging situation, of course, the amount of charge increases. But during discharging, of course, it goes down exponentially, which makes sense, right? Then, of course, if you're interested again in delta VC or delta VR, the same things can be used. Again, once you found one of these quantities, the rest can be found easily using the facts which we discussed before, right? So now, but anyway, let me mention it. So, for example, delta V across the resistor will be equal to what? I, which is of course a function of time, times R. And of course, also potential difference across the resistor and potential difference across the capacitor, they're the same, right? Because there's nothing else, right? So of course, absolute value must be the same. So delta V across C, right? Okay, so that's what I wanted just to mention about discharging situation, right? And most of the problems are going to be about discharging case. But again, read carefully, because I think I remember on one of the exams, I gave a problem about, I don't remember, let's say discharging, and some students used equations for the charging case, right? So it's, yeah, it doesn't sound good, right? If you don't see the situation, right, it doesn't sound good. Okay, and again, what's the sort of major difference here, current and charge related to the minus, here to the plus? Let me switch back to the presentation, and let's answer at least that second clicker question, a conceptual question, right? So what do we have here? We have two circuits, circuit A and circuit B, both of them discharging cases. You see, we have first initially capacitors are full, capacitor A is full, capacitor B is full, and then gets discharged through those resistors, 2 ohms and 3 ohms. Capacitance are given, 6 microfarad, 5 microfarad. So which capacitor discharges faster when switches are closed? Of course, closed at the same time. Right. So give it a try. So which capacitor discharges faster? In order to answer this question, we just need to look at the time constants. As I already mentioned several times, the time constant allows us to compare different circuits in terms of which one faster charges or discharges. So the smaller time constant, the faster capacitor is charged or discharged. So let's calculate time constants and see which one is smaller. The smaller time constant, the faster circuit behaves, faster charged and faster discharged, right? Okay, so now let's see. In the first case, in the case A, so RC time constant, it's a product of resistance and capacitance. So in the first case, 6 microfarad times 2 ohm, so that will be 12 microseconds, right? Tau 1, 12 microsecond. In the second, 5 microfarad times 3 ohms, so 15 microseconds. So obviously, first time constant is smaller than the second one. Of course, it means that circuit A, capacitor A, in this case, discharges faster. Right? Discharges faster. So that's why, again, that's why basically time constants are important, right? So you can quickly analyze behavior of circuits, right? Okay, so capacitor A, and most of you answered. I picked that option.